Hello, we are back after some time. Let's start. Implement a stack, last in, first out. Using only two queues, implemented stack should support all functions of a normal stack. Stack using queue. क्यू में क्या होता है अपन जो डाला पहले वही पहले निकल जाएगा है ना. पुश करे तो मुझे क्यू से इम्प्लीमेंट करना है. Try to work with some examples.
So with this video, we will be starting off with the stack and queue playlist. Again, this is So with this video, we will be starting off with the stack and queue playlist. Again, this is a continuation of the Strivers A to Z DSA course. If you haven't checked it out yet, you're missing out on something. So I'll be giving out the link in the description. Make sure you check it out. We were starting off the normal thing. Hey, welcome back to the channel. I hope you guys are doing extremely well. So this will be an introductory video about stack and queue and what all will I be covering up. I'll be covered first in, first out. Why? I had a fold, you popped it out, so I don't have an net. Along with this, we'll be taking a couple of, but this time when the start goes ahead, it goes, yep, will be containing, what does pop mean? What you can 3. Increase in current size. Done and dusted. So this is how the element was 1. So what you can say is top of data, top of value. If you do that, top of value, you will get that value. Perfect. After that, I'm asking you to pop out. What does pop mean? What you can do is temporary equal to top. So what I'm going to do is, how do I push x into it? This is not the first element. Otherwise, you would have been at none. This is the second or third or fourth, some of that level element. So what you will do is you'll take the end. You'll take the end and you will take its next and point it to this one. And once that is done, you can say, hey, end, not to the start, not to the start, just to the end. Can you move ahead? Done. After that, I'm asking you to push 3. Again, I'll take an element 3. And I will, once that is done, the node is created. I'll ask the end to point to this one. And once that is done, I'll take the end and I'll, okay, so time to write down the pseudocode. Again, and you'll have to make sure that this queue behaves as a stack. Now, if you remember, a stack is nothing but a last in, first out data structure, whereas the queue is a first in, first out data structure. So obviously, if we use the queue directly, it's not going to work. I'll have to modify the queue. I'll have to do some extra operations so that it ends up behaving as a stack data structure. If you know the stack data structure, you have to make sure the top operation returns me the last entered element, and the top deletes the last entered element. That is what I have to keep in mind. Perfect. Go to the first operation, push 4. We'll do that. At this moment, it is okay because if I'm pushing 4, if I'm asking the top, it will give me 4, which is okay. For stack, the top element is 4 as of now. Okay. What's the next one? Pushing 9. This is the moment we'll have to think. Till this moment, if I ask you the top element, the queue will return you a 4. The queue will return you a 4, right? Which is wrong because the stack means last in, first out. And the last in element was 9. I need 9. I don't need 4. So I have to make it behave in that way that the top element is 9 and not 4. You can get the intuition. Reverse it. Reverse the queue. Yes. So what I'll do is, whatever was the number of elements before. Before 9, I had 1 element. So I'll just pick it up. And I'll put it over here. Done. So I've taken up 1 element and put it over there. Now, if I ask you, after this operation, give me the top. The queue says my top is 9, which is okay. That's the stack stop. Okay. Let's do the next one. Push off 2. So if I push 2, it goes over here. In a queue, it will go over there. So after these many operations, if I ask you the top, it will give me 9, which is wrong. Right? So what I will do is, before this 2, I had 2 elements. I will bring it here. So what you will do is, first, you'll take out 9 and you'll place it here. After that, you'll take out 4 and you'll place it here. Done. So now, if I ask you, does it look like a stack? Top element is 2, which is, yeah. After that, the top element is 9. After that, the top element is 4. Okay, next. push of 5. So if I push, most of the queue implementation was using a start and an end. Why was that? For start, I know what looking at the end will be where. Have you understood this? So the next thing is to implement a queue using a stack data structure. And most of the stack implementations, you did see that I was using a single variable top. And in most of the queue implementation, I was using a start and an end. Why was that? For stack, I know one thing, it is a LIFO mechanism data structure. So I'll be entering at the end, and whenever there is a call for getting the top, I'll be taking out from the end itself. But whenever it comes to queue data structure, I will be entering at the end, like I'll be pushing it into the end. But whenever there's a call for the top, I'll be taking out from the back, right? So that is why in all the queue implementations, be it arrays, be it linked list, I was using start and an end. Over here as well, I'll be using two stacks. So the problem statement is I have to simulate the mechanism of queue using stack data structure. I cannot use a queue data structure. I'll have to kind of replicate the similar behavior using stack data structures. So what I will be doing is I'll be taking two stacks, S1 and S2. So what is the first operation? Push 4. Now this is how the push operation will look like. Again, you will have to know it, or you'll have to think a lot during the interview. So what you will be doing as the first step is whatever is there in S1, you'll be putting it into S2. There is nothing, so you can stop. And you'll put the variable that has to be entered into S1. So I'll be putting it over here. And after that, for the third step, everything from S2 to S1. Not needed. Okay. Push 2. Now realize why am I following these three steps? Understand. I'm asking you to push 2 and you push it into the stack, right? And the queue comes and says, get me the top. So what you will do is you'll give the 2. You'll give out the 2 because stack's top is 2. But queue is a FIFO mechanism. So it will require 4 because that was the first entered element. You're not getting it. So for the same reason, whenever I'm asking you to push 2, what you'll be doing is you'll be taking out this 4. Yes, you'll be taking out this 4. You'll be putting it into S2. Then you'll be taking this 2, putting it into S1. Then on the third step, you'll be taking out everything from S2 and putting it back. So now, at this point, if someone comes out and asks you, hey, give me the top element, you can give out 4 because that is how it is. 4 first and then 2. And it is maintained. Let's check out one more example. Pushing 3. So if I've been asked to push 3, what I'll do is I'll take the first element and put it over here. Then I'll take the second element and I'll put it over here. Done. After that, I'll take the 3 and I'll put it, which is the second step. And the third step is get back everything, which is first 2 and then 4. First 2 and then 4. Done. Again, if you see it is following. It is following. 4, 2. 2 3 4 2 3, just following. Okay, what's the next one? Push 5. Where's the first step? Oh, properly see. Okay. Oh, you can straight it. Take out 3, take out 5, push it in, and then push 6 over here, and get it back. So I'm getting back first 5, then 3. So again ask you the top. Oh, that's not 3. Which is makes sense. It does that. First 5, then 3. First 2 elements were gone, and after that you had 3. That makes sense. Super simple. 3 steps, and you're done. So if I have to write down the method, it will be class. I need S2 in order to store the element so that I can get it back. So we're writing the push operation. So maybe what I can do is element from the top. He's like, why not? And then can you just pop it out so that I can get the next element? Done. That is step 1. For step 2, S1 dot push of X. Done. For step 3, get everything back from S2. So till S2 has something, I can say S1 dot push of S2 dot front or top or whatever you call it. And after that, can you just pop it out? And that is done for the push. Can I get the top? Super simple it will be. You can simply say S1 dot top will be your answer. And can I do a pop? Yes, you can simply do S1 dot pop. If you need a size, S1 dot size. So what is the time complexity? The time complexity for the push operation is a big O of 2n. If you carefully notice, it is a big O of 2n because I'm doing S1 to S2 over here, another S2 to S1 over here, right? So it is taking a lot of time as big O of 2n. What about the space? I'm using a big O of 2 into dynamic space because I'm using 2 stacks. Got it? So this will be expensive if I have a lot of push operations in my problem statement because I'm taking a lot of time to push. If there are a bunch of push operations, this might be expensive. So depending on the problem statement, if your problem has very limited push operations, then you can use it. But if it has significantly higher push operations than the top and the pop, then we'll be going for the approach 2, where the push is going to take lesser time and the top and pop are going to take more time. So the second approach will be focusing on optimizing the push operations, assuming that we are doing a lot of push operation, and we will be making the pop and the top operation expensive. Again, I've written down the algorithm on the right over here. It's a very simple, straightforward algorithm. There's no intuition behind it. The moment you see me doing a trial, you'll be like, ah, that was easy, right? So there's no intuition. It's very simple, basic maths or basic implementation. So let's quickly try to do it. Again, we'll be taking 2 stacks. One is going to be S1, while the other one will be called as S2. Okay. First thing, push 2. We'll keep it very simple. Just push it on S1. Push 3. Push it on S1. Push 4. Push it on S1. Push 5. Push it on S1. Now, at this moment, if someone is coming up and saying top, you actually cannot get it from S1 because according to the Q data structure, this is the first element. But if you do a stack 1 dot top, you'll get this element. So what you should be doing is this should be at the first. So this is the reason. This is the reason. Whenever there is a top operation, what I will do is if there's nothing in S2, I'll be taking everything from S1 to S2, everything from S1 to S2. Why did I do that? You'll understand. First thing, 5 will go off. Next thing, 4 will go off. Next thing, 3 will go off. Next thing, 2 will go off. So I've taken everything from S1 to S2. At this point, you will see that 2, 3, 4, 5, this should have been the order, and this is the order in S2. So if someone is asking you the top, you can straight away give by saying take 2, take 2. So I'll be given 2. I will not get it back to S1. Why? You'll understand. Again, someone is asking the top. I've done the transfer. So I can again take 2. So that is why I'm saying if there are some elements in S2, that means the transfer was done. And if there are some, why don't you just give me the top? So I have optimized it significantly. So what I'll do is again get the 2. Perfect. At this time, when someone is asking me to pop, technically the 2 should go, and that is the one that will go. If you look at the pop, if S2 has something, I just take. you'll understand. So again, someone's asking the prop. I've done the transfer. I've done the transfer. So again take two. So that is why I'm saying if there are some elements in S2, that means the transfer was done. And if there are some, why don't you just give me the top? So I have optimized it significantly. So what I'll do is again get the two. Perfect. And this time, when someone is asking me to pop, technically the two should go, and that is the one that will go. If you look at the pop, if S2 has something, I just take it off. So what will happen is the two will go off. So pop is also done. Right after this, I'm asking you to push one. Remember, two is gone, so you can just cross it off. Two is gone. I'm asking you to push one. So what you do is you'll push one into S1. Okay, and done. After that, I'm asking you to pop. So do you need to put it back? No, because you have three. You have three, right? And that is what pop checks. If there are still elements in S2, it means the order is maintained. I can still take it up. So for this pop, what I'll do is I'll take out a three. For this, oh my bad, this pop is done. And for this pop, I'll take out this four. And for this pop, I'll take out this five. Okay, done. So basically, what has happened is three. 3 has gone, 4 has gone, 5 has gone. After this, I've been asked for the top. I've been asked for the top. This is where I'm saying, do we still have elements in order? He says, no. Get everything from S1. Get everything from S1. So I take it from S1, put it back. And now when I'm being asked to pop, I'll just take it off. Got it? I once I do the transfer and let the order flow in, right? For the top and pop. And I keep the push elements with me. That is how we can easily implement the approach 2. So what I'll be doing is I'll be super quickly writing down the pseudocode. So class of Q. Again, very simple. I'll be taking stack of I and T with an S1, with an S2. Done. Right after this, we'll have to implement a push. Push is super simple. I'll just do an S2 dot push of X. Pop is where everything is done. Very simple. If S2 is not empty. So I can simply do a S2 dot pop. Otherwise, this is where the game starts. I say everything from S1. I take everything from S1 and I say S2 dot push S1 dot top. At the same time, I can say S1 dot pop. So I've taken everything. Once I've taken everything, I can say S2 dot pop property latest element. Pop is done. Similarly, can I write top? I can. What will be top? Top will be same if S2 dot empty. Can you do an S2 is not empty? So we're done with pop. Now the next thing is top. Can I do a similar thing? Yes. If S2 is non-empty, which means not equal to 0, I can straight away return S2 dot top. Otherwise, I'll have to take out everything from S1, which is S1 dot size. Till I have something, can I say S2 dot push S1 dot top? Yes, I can. And I can say S1 dot pop. At the end of the day, I can return S2 dot top. That's it. Just return this, and that will be your element. What is the time complexity if I have to analyze? I'm doing a push in big O of 1, and occasionally I'm taking a big O of 1 where I'm transferring S1 to S2. Occasionally over here also I'm taking a big O of n when I'm transferring from S1 to S2. That is occasionally, not always. So I've optimized significantly. But yes, I'm using 2 stacks, so 2 into dynamic space, whatever we need. So yeah, that is it for this one. I hope I've covered up everything that we planned to do at the start. Let's go back and check it out.
display zero index integer is so a subset of index. For each number in num1, find the index such that num1 का I num1 का वो element is equal to multiply वो element and element of num2.
So let's continue with the stack and cube playlist. Today, starting off, everyone come back to the channel. I hope you guys are doing extremely well. So the problem that we will be solving today is next greater element. So from this problem onwards, we'll be starting off with monotonic stack. So what is monotonic stack? Till now, I've been using stack to store elements. But the moment we use stack to store elements in a specific order, that is when we call it as a monotonic stack. So maybe I can store elements in an increasing order in the stack, or maybe in a decreasing order, or maybe in some other order. So whenever we are following a specific order, that's when we call it as a monotonic stack. Got it? So this problem is next greater element, or commonly known as NGE. So what is the problem statement? It's stating that you're given an array for every element. For every element in the array, you have to tell me which one is the next greater element, as the name is telling you what it is all about. So you basically stand at 6, and then you look at the next elements. Is 0 greater than 6? No, it is not. Is 8 greater than 6? Yes, it is. The first element that is greater than the element. So you see that 8 is the NGE of 6. So what I can do is I can write 8. If you stand at 0 and if you look at the right, I do not have, I have a 3 which is greater than 1. This array is what you will have to return. Straightforward, isn't it? What is the first approach that comes to my mind? For every element, go to the right and find the next greater element. Okay, fine. So in order to traverse for every element, I know one thing for sure. I need a loop 0 n minus 1. So I'll iterate on the array. I'll go to every element. Now for every element, I need the next greater element. So one thing I know for sure, the next greater element will be on the right. Thereby, I'll start from the next index, which is I plus 1. I'll go until n minus 1. Again, straightforward. If at any moment I say array, maybe I need an array, and then you can say that NGE follow pens. Again, you can input don't pen here about. Again, this space is not used in order to solve the problem. Rather, it is used to return the answer. So it is something that you cannot avoid. At this moment, the interviewer will not be happy with the big of n square. He'll ask you to optimize it. So we need to optimize big of n square. That clearly gives us an indication that we're looking something around big of n or big of 2 and big of 3n or n log n, right? Fine. So imagine you're standing at this element 3. I'm asking you, what is the NGE of 3? Now, in order to know the next greater element of 3, you will look towards the right. So you should be knowing the right elements. You should be knowing the right elements beforehand. But the generic way of traversal is starting from the left. You start from here, then you go here, then you go here. So there is no way that when you reach 3, you would be knowing what are the elements on the right. There is no way when you reach 3, you'll be knowing what are the elements on the right. So will it not be better if you traverse from the back? If you traverse from the back and if you reach At that moment, you'll be knowing what are the elements on the right, and that is what you need. The first optimization or first thought process that I can think of is maybe I'll start from the back, so that at any particular index, I will be knowing what are the elements on the right, and then I can think of a solution. Then I can think of a solution. Okay, now I know where to start from. That is the back traversal. So what I will do is I'll be taking a stack, and this stack will be storing elements in a specific order. Why, you'll understand as I explain. The first element is 6. So what you do is you look in the stack and you don't have anything. If you do not have anything, that means there are no right elements. So what you can do is you can simply say -1 to it. You can simply say -1 to it. Got it? What after that? After that, you take the element 6 and you put it into the stack and then you move back. So now when you move back to 4, you look in the stack and you see that there is a 6. There is a 6. So you can say that that can be my next great element because 6 is greater than 4. So you say, okay, I have my next great element. And you take 4 and you put it into the stack. After that, you move back. Now you have something as 2. Again, you look into the stack and you have a 4, which can be your next great element or which is your next great element. So you take 4 and you place it over here. Again, you take 2, put it into the stack and you move back. This time you're at 1 and you look into the stack and the topmost element is 2. So you say that, okay, this is my next great element. I'll take 1 and put it back and I'll move across 3. I'll move across 3. Now this is something where you need to understand. What is stack storing as of now? It's storing something of a length, like a 6 size. Just imagine light poles. Light poles of a length 6. After that, it is storing something of a length 4. After that, something of a length 2. And after that, something of a length 1. Now suddenly, you are at 3. Suddenly, you are at 3, which is typically, you can say, somewhere around this, correct? Now tell me one thing. For this 3, which will be your next great element? It will be 4. For that, you'll have to take them out. Now you might say, if I take them out for the future elements, I will lose out on some of the right elements. No, you'll not lose out. Let me explain you why. Imagine I come up with something like 1 over here. After 3, just imagine.
Oh.
Just imagine. After 3, there's an element which is of length 1. Tell me one thing. Even if you lose out on 1 and 2 in order to get 4, because in order to get 4, you have to take out 1, 2. You have to take out 1, 2, so that's gone. Just imagine this is gone. For this 1, if this 3 is your answer, will 1 and 2 contribute to your answer? The answer is no. It will never contribute because for an element like 1, if 3 is the answer, 1 and 2 can never contribute because this is a light pole which sees this, and beyond this, it can never see this. Beyond this, it can only see a larger element. Beyond this, it can only see a larger element. And beyond this, a larger element. So will it not be sensible to store the elements in this decreasing order, in the decreasing order, which is like 6, 4, 2, 1. And now when 3 came up, you don't need to store 1 and 2. You don't need to store 1 and 2 because if 3 is the answer of someone, 1 and 2 can never be. 1 and 2 can never be. Got it? Perfect. So what I'll do is, I'm at 3, right? I'm at 3. I'm saying 1 can never be my answer because that is lesser. Like, okay, remove. Can 2 be your answer? No. Remove. Can 4 be your answer? Yes. So what you say is, 4 is my answer. Take up 3 and put it into your stack. After that, move across.
Bro, logic, my. 4 के लिए 4 के लिए साइज वगैरह क्या नहीं zero stack okay some other element हो अगर current top is greater than नहीं है This result will have
close to 5. Now when you're at 5, you're again looking at 3, no. You're looking at 4, no. So what you do is you basically take both of them. 6 can be your answer. So you write 6 and you put back 5. After that, you move to 2. Now when you move to 2, the top of the stack is your answer. So you just take it across. After that, you take 2, put it back, and you move back. 1, the top of the stack is your answer. 2, again you take 1, put it back, and you move back. This time when you're at 3, can 1 be your answer? No. Can 2 be your answer? No. So you take both of them out. You take all the elements which are lesser than that element. And after that, 5 can be your answer. So you write 5 and you put back 3 and you move back. You're at 5. When you're at 5, can 3 be your answer? No. Can 5 be your answer? No. You're looking for data. So I'll end up deleting both of them. Can 6 be your answer? Yes. So I write 6. After this, I insert 5 and I'll move back. When I'm at 12, I look onto the stack. No. So both of them can go off. And the stack will be empty. And the stack is empty. You say that the answer is -1 and you put back 12. And now you go back. 4, the top of the stack is 12. That can be your answer. Put back 4 and then go off. You're done. And this is your next greater element. This is your answer. Yes. So what did I do over here? I did use a monotonic stack. Why? Because I was storing the elements in a specific order. And that specific order was the decreasing order. Yes, the decreasing order. If you carefully notice, I stored 6, which is typically, let's say, here. And I stored 5, let's say, typically here. And I stored 2, let's say, typically 2 is here. And I stored 1, which is typically here. So that was a decreasing order, right? That was a decreasing order. And then whenever there was a 3 would have been somewhere here. That order would have been distorted. That is why what I did was I removed 2 and 1 so that the decreasing order is still maintained. So that the decreasing order is still maintained because I'm decreasing it. Got it? So I hope you got you got the concept of next great element, the intuition. The intuition comes from the light poles. If you're a human being and you're looking on the rightward direction, it's obvious that you'll only see increasing stuff. Nothing in between that. Nothing in between them. You'll just see the increasing curve. Correct. So the intuition comes from there. Perfect. So time to write down the pseudocode. So we will be returning a list or a vector according to the language that you're writing in. So I'll be returning a list of integer. I have to find the next greater element. So what will I be given? I'll be given an array for sure. Okay, so what do I need? I need an array which stores all the next greater elements. So maybe an NGE of size n into 2. Perfect. I need to traverse backwards. And I also need a stack. So maybe I can define a stack st. I'm not writing the syntax. It has pseudocode. So let's quickly traverse from the back. So that is going to start from n minus 1 till 0, backward traversal. So I know one thing. If there are elements in the stack, and there's something which is smaller, highest take them off. So I say, hey, listen, if the stack has elements, that is very, if the stack is not empty, and the stack.top is something which is lesser than equal to, very important. You have to remove the lesser and the equal elements as well. Lesser than equal to array of I. So can you please do me a favor? Just do a stack.pop and keep on doing till the stack is either empty or you remove all the smaller elements. Once this is done, that means you remove the smaller elements for sure. Correct? After this, what you say is, okay, listen, if the stack is empty now, because after removing, if the stack doesn't have anything, which means all the elements in the stack were smaller, which clearly tells me that NGE of I should be minus 1. Or else the NGE of I should be array or rather the stack.top, isn't it? Because that is the element that was not removed. Why? Because it was greater. Okay, done. What after this? I say stack dot push what? The current element. And the for loop is completed. And once that is completed, you end up returning the NGE list. Perfect. Am I done? I think I'm done. It's time to analyze the time complexity. What do you think? A lot of people will say there's still big of n square, a big of n here, and then you're iterating on the stacks, another big of n over here. No, it's not. Instead, it is a big of 2n at the worst possible case. Big of 2n at the worst possible case. Why? So imagine, like, understand, this is for sure running for big of n. But if I ask you, how many times is the while loop running? What will be that? Is it running for n every time? Is it running for n every time? No, it is not. It is not running for n every time. Correct? You need to understand this. Okay? Then how many times is it running? So if you look at the example, what is the stack containing? Stack is containing nothing but these elements. So whenever you are at 3, what the stack contained was 4 elements. So at the worst possible scenario, you'll end up removing 4 elements. You'll end up removing 4 elements for this element, right? So throughout the journey, you might remove this from the stack. Throughout the journey, this is what at max you can remove from the stack. So can I say this stack.pop at max can be performed for big of n? Not beyond it, because I'll only remove the elements that I've inserted into the stack, and I've only inserted at max of n elements. So I'll remove at max of big of n elements itself. Maybe sometimes I remove 3 elements, maybe sometimes I remove 2, maybe sometimes I remove 1. But the addition of it will sum up to be big of n. Got it? Okay. So that is why the time complexity at the worst possible case will be big of n for this one, and throughout it might end up taking a big of n, which ends up making it a big of 2n. Okay, what about the space complexity? I'm using a stack, so that's a big of n. And I'm using another big of n in order to store the answer. Again, this is something which I'll have to use in order to return the answer. I don't want to modify the given input. We don't do that in an interview. We usually use a different array in order to store all my answers. So that will be the time complexity and the space complexity. I hope you understood the thought process of traversing from the back. I hope you understood the intuition of storing in a decreasing order the light pool concept. Got it? That'll
I think that's all for today. Bye bye.